Sunspot 2728. Somebody must have heard us. Indeed, it was named 2728. Who would have thunk it? There's a great image of it forming there. Check it out. Just blasting those magnetic fields out of the way and exposing the solar black body. Cheers. 304 angstroms. There you have it. It's got beta class magnetic fields. And we've got some filaments. No apparent CMEs. Let's look at the magnetic lines. And they are completely anomalous. Apparently the AIA every line is coming straight out of the sunspot. We're not sure how this anomaly happens, but it does happen occasionally. Moving on to the earthquake situation. Check out quakes.globalincidentmap.com. And no, they're not paying me to say this. Let's go back 11 hours. Geez, we got a 5.1 in Venezuela. 4.2 in India. 4.3 in Russia, a 5.8 in New Zealand, probably caused some damage, although they are built for that there. 4.3 in Russia, 4.8 in Tonga, 4.6 in Colombia, 4.5 in Greece, a 4.6, which brings us to 5 hours ago, 4 hours ago. It looks like that's probably only one quake. Colombia, a 6.0, the largest quake on the world in weeks. Little aftershock, 4.4 and a 4.2 in Colombia. Another 5.6 in New Zealand, a 4.4 in Afghanistan. So a little uptick in earthquake activity there. Let's look at some space weather data at spaceweathernews.com. Also not paying me to make this report. There's your X-ray flux. And no flares since yesterday. We got a choppy BTBZ, which is often associated with earthquakes. Keep that in mind. See all those spikes? Especially a negative BZ tends to really be associated with earthquakes. Phi angle shifting around, no signal there. Looks like we've got some choppiness in the solar wind density also. Around 10 protons per cubic centimeter. Small uptick in the wind speed, although that's kind of jumping around too. What, 370 kilometers per second? You can see these heavy magnetometer spikes here. And the KP is at 1 still, as it was yesterday. No increase in the electron flux, a little surprising there. And keeping an eye on that. Totally wrong about the prediction of that going up. So, eyes on that. And the F2 ionosphere layer looks highly discharged. Look at that. A tiny area of 9 megahertz. Heavily discharged ionosphere. Aurora forecast is looking pretty average. Let's move on to some other stuff. Check out solarham.com for the active region. And there you go. There's your beta class magnetic fields. You can see there's some magnetic mixing going on. There's your intensity gram. You can see the umbra. At least 5 or so. And there you can see the magnetic mixing. Not bad. Not super powerful, but keeping an eye on it. Not sure whether that's degrading or not. Let's take a look at the geospace magnetic perturbation map. Not expecting big perturbations here, but let's just look at it anyway since we don't do this every day. In any case, it is a pretty cool graphic, especially when it loads. And there you have it. We'll let that play through. This geospace model, courtesy of University of Michigan Space Weather Prediction Center. There's that. Now, let's look at the Space Weather Enthusiast dashboard. Saw some interesting stuff here. First of all, the X-ray imager. No surprise there. Those X-rays are and have been coming out of that sunspot. Thank you, Sunspot 2728. Oh, that was interesting. Some kind of a weird... Let's let that play through again. Looked like a little oddity in the northeastern corner of that sunspot, right at the beginning of the animation. I think that was a filament that came down like this. Anyway, links to that below. Let's also look at the C3, as we saw something interesting there too. A comet looking like it's on a suicide mission. Check it out. As Mercury passes in front of the disk, so does the comet. Will it make it out? We'll be watching. It got close enough to the C3 that we can actually see it on the C2 also. The last few frames of this GIF, you'll see it popping in from the bottom. Check it out. Comet making its appearance. Nice. And let's just look at some weather maps here. Talk about the global electric circuit a little bit. What do we got? Water vapor map. We got a whole lot of nothing. All right, so let's take a look at the NASA GOES water vapor map here. Let's see, we've got a low pressure area here. Low pressure area here. Here we've got high pressure. And some heavy high pressure down here, trying to become anticyclonic. And what's the point? Well, the point is that your weather is electric, even the non-lightning portion. Your high pressure zone represents a positive charge, and it represents a pushing force. Basically pushing down on the atmosphere, high pressure, right? In a low pressure zone, you've got the opposite. You've got a negative charge, and you've got a sucking force, meaning the primary force is coming out of the atmosphere. This has huge implications on how weather patterns interact with each other. Now, let's look at a great example of a high pressure zone over New Mexico especially. You can see all these sheets of different water density here. And you see all those lines. Now, some of those lines are going to be lines on which cirrus clouds form, as these do represent ionization paths to some degree. Just keep in mind that the bright spots are drier and the dark spots are wetter in this part of the range. Remember, this air is more massive also. Excuse me. And last but not least, you can see a whole bunch of parallel lines in here where the water vapor is moving around. That is because of electrical potential, electromagnetic fields, electric current, whatever you want to call it. That's what's forming those parallel lines. And if you think those are chemtrails formed by aircraft, for instance, right here, see those parallel lines? Those are probably forming similar clouds in the sky. Meanwhile, people are going up and looking and saying, oh, look, it's chemtrails. Only one problem with that theory. You wouldn't be able to see something like that from this map because, see that? Resolution 2 kilometers. So just in case you thought somebody was making a 2-kilometer wide chemtrail, yeah. Since they're not a thing, at least as sprayed from aircraft, here's a perfectly normal high-pressure system, attenuated by normal atmospheric factors and unexpected factors, electromagnetic fields. Let's take one more look here at the shortwave radiation view of the same area, which, since it's dark in New Mexico right now, we can't use a visible satellite, but this will give you some approximation of what the clouds are. And no surprise, we've got cirrus clouds forming in parallel formations. See that? See all those vertical lines? And what's going on with those vertical lines? Hall currents. And just to give you some idea of what that means, well, you've got solar protons, mainly, coming in from the sun. These get split at the poles into field-aligned currents, as you see in the diagram. These are Birkeland currents coming in and going out, exchanging charge both directions, into the Earth and out of the Earth. Equalizing said Birkeland currents, we have Peterson currents, which travel back and forth between the Birkeland currents at the poles. Now, some of that charge is going to spill out because the atmosphere is a semiconductor, and those secondary circular currents that are going to circle the field-aligned currents and separate the Peterson currents on each side, those are called Hall currents. And it's no coincidence that we see clouds forming perpendicular to the Hall currents. Just thought I'd share, the clouds are electric. In any case, thanks everybody for watching. Please don't forget to like and subscribe the videos. We'll be doing it daily. We'll be staring at the sun. We'll be staring at sunspots. And remember, when you're pushing the boundaries of science, don't drink. And if you drink, push the boundaries of science anyway.